Hello and welcome back, and thank you very much for watching this lecture video. In this lecture, we're going to go through activator versus deactivator substituent. So we have electrophilic substitution reaction, and we want to know when one substituent is going to be activator or deactivator. Is it going to speed the reaction? Is it going to speed the reaction or slow the reaction? Okay, the activator is going to add some electron density to the ring. So I'm going to draw this vector. And activator is giving electron density to the ring. So I'm going to say the electron density here, the negative charge for the ring, will go up. And now that you are adding electrophile to it, electrophile will see plenty electron density inside the ring, or we can say the ring, because it has more electron density, very soon it's going to go after the electrophile, and the reaction will be faster than benzene molecule. Okay, because instead of hydrogen, we have something that donating electron to the ring. The deactivator is pulling electron density. So this time the vector is pointing up, and that means that we are creating a positive charge inside the ring, or we are stealing electron density from the ring. Now the ring got poor of electron, and so it's not, it doesn't have much any electron left to share with the electrophile. So I'm going to say in this case the reaction will be slower than benzene ring, okay, because some of the electron density got pulled by the deactivator even before we see the electrophile. And remember, electrophile is looking for electron, and the ring already shares some of the electron density with the deactivator substituent. Okay, the activator is donating electron density to the ring. So now we will have more electron density here when the electrophile is reaching the ring, and it can see more electron density on the ortho position. So here, ortho position, and also the para position. So our substituent, technically, our electrophile might show up here. It will show up there, or it might get attached inside the para position. So para or ortho. Okay. So how about this? Activator, activator will enrich the ortho and para positions. And whenever the electrophile is reaching the ring, and the electrophile will reach the ring through either the ortho or a para position. That means you will get either ortho or para products. While the deactivator, it will pull electron density. It will pull electron density from the ring, and it will pull it mainly from the ortho and the para. From the ortho and para. What does it mean? It means the meta position stayed like untouched, not 100%, but I will say there is more electron density on the meta position. So the addition, technical addition of the electrophile, it will happen through the meta position, and we will have E attached through the meta position. Okay, now, if I want to summarize whatever I said until now, activator is directing to ortho and para position, and deactivator is directing to the meta position. Okay, except the halide. Halide are deactivator. Okay, they are deactivator. So let's write here halide. They are deactivator, but they direct to ortho and para. So be careful about this one. Okay. Yes, they are deactivator. They are supposed to lead to the meta position, but this is exception when it comes to halide. Halide, they are deactivator. They will pull electron density from the ring, but they will activate the ortho and para position. What's the reason behind it? Mainly, it has to do with the lone pair on the halide, and we will talk about that one very soon. Okay. How do I know whether the substituent I'm dealing with is an activator or deactivator? Or how about this? Is it the electron donating group or electron withdrawing group? Okay, so I want to know whether I'm dealing with electron withdrawing group or electron donating group. Okay, electron donating group, if you are dealing with alkyl groups with sp3 hybridization, they will donate electron density to the ring. Okay, remember, ring, any carbon inside the ring, it has sp2 hybridization. If you attached anything, any alkyl group to it, let's say tertiary butyl, for example, tertiary butyl, it will have sp3 hybridization. Electronegativity of sp2 is higher than electronegativity of sp3. What does it mean? It means the alkyl group will give electron to the ring. Okay, alkyl group will give the will give electron to the ring. So if you put R here, it will give electron to the ring. And now tertiary, it will give more electron density than, say, we have hydrogen here. This is going to be isopropyl, and then stronger than. Next one, it will be ethyl. And ethyl is more electron donating, in the stronger electron donating group than methyl, because it has only 3 hydrogens and it doesn't have carbon anymore. So I'm going to say tertiary butyl, it has more power to donate electron than any of other substituents. And donating here, okay, donating here is through induction effect. Okay, there is no resonance here. It's mainly induction. Okay, mainly induction. And next one is the heteroatom. We have heteroatom with a lone pair. Okay, if you have a substituent that is a heteroatom and it has a lone pair on it, it will share that lone pair with the ring and it will enrich the ring. So, for example, I have this group. Here I have nitrogen attached to 2 hydrogens. That nitrogen, it has a lone pair. Okay, if you have a heteroatom like nitrogen, say nitrogen, oxygen, or say sulfur, okay, phosphorus, and they have a lone pair, okay, with a lone pair. This group will donate electron density to the ring, and they will enrich the electron density. So we call them activator. Okay, how do I know whether this one is going to be activator or deactivator? Just simply ask yourself. Am I dealing with heteroatom in this case? Yes. Next thing, do I have a lone pair? If you have a lone pair, on a heteroatom, it will be electron donating group. Okay, electron donating group, and it will share this electron through making double bond with the ring, and that way it will enrich it. Okay, let me prove it for you. So imagine you have this, and now we're going to make a double bond with nitrogen, and we have 2 hydrogens here. Okay, now what happened? Those 2 electrons now shared with carbon, and this one it will move here. So now I will have 2 electrons on that carbon. This carbon will have -1 charge, and remember we do have double bond there. So what happened? From a neutron ring, I got a ring with a negative charge. Did I increase the charge on the ring? Yes, and so I have the right to call it activator. Okay, I have 3 substituents, and I want to order them based on their strength. Okay, the first one is just simply alkyl group. So this one is alkyl group. We have carbon with sp3 hybridization. Okay, we have 4 carbons with sp3 hybridization. Next one, we have heteroatom with a lone pair. And last one, yes, again, we have a lone pair, but we have this group attached to it. And that group, it has a carbon. Okay, we have a carbon there. That carbon, it has sp2 hybridization. Okay, so now let's order them. Okay, if you have a heteroatom with a lone pair sitting on it, regardless of how many R group or hydrogen atom attached to it, that's going to be a strong electron donating group. So this one, it will be number 1. Okay, so if I want to order them, this one is going to be number 1. Next one, okay. Now, what's the difference between number 1 and, let's say, this? Oh, no, third one. I'm going to call it number 2 here. And what's the difference between them? The difference between them, we do have a nitrogen, has a lone pair. Yes, instead of R, we have hydrogen. Okay, but we have one, like our R, this R technically got replaced by a substituent that it has sp2 hybridization. This substituent is going to pull some electron density. Okay, so it will pull some electron density to itself. Why? Because we have a carbon with sp2 hybridization. So number 2, it will be weaker than number 1 because of hybridization of the carbon. So this one, it will be number 2. And that one, it will be number 3. Okay, so and last one, it will be the alkyl group. And that's going to be the last one. Okay, and that's the order for the strength. Okay, so go with lone pair. If there's a lone pair, that's going to be the strongest one. Now, do you have sp2 hybridization? Lone pair and sp2 hybridization. If that's the case, then that's going to be number 2. And if you don't have a lone pair, it's just alkyl group and no electronegative attached to it, that's going to be still electron donating, but it will be the weakest one. Okay, now how about electron withdrawing group? If you take alkyl group and replace the hydrogen atoms by say by, for example, electronegative elements like a fluoride, chloride, bromide, whatever. And so say I replace 3 of them by fluoride. That's going to be electron withdrawing group. Now, if you replace only 2 of them, okay, again, still it will be electron withdrawing group, but weaker than the previous one. Okay, and this one, in this case, I'm going to keep only 1 of the fluoride and replace this by, okay, replace 2 of the fluoride by hydrogen. This one, it will be electron and electron withdrawing group. Why? Because fluorine is going to pull electron density, while hydrogen is giving electron density. Okay, so those are electron withdrawing group. And last one, if you replace all of them by hydrogen, in that case, this one, it will be electron donating group. Be careful, electron donating group. Well, those 3 are electron withdrawing group. Okay, so alkyl group with halide attached to it, it will be electron withdrawing group, and effect it will be through induction. And next one, what if we have a heteroatom with a lone pair? Again, that's because of electronegativity, it will be with electron withdrawing group. And example is this. Say, for example, NO2. This one, it will be electron withdrawing group. Okay, what's the reason behind it? Because you have nitrogen. Okay. You have nitrogen that attached to 2 oxygen. And nitrogen has a positive charge. So nitrogen is going to pull electron density from the ring. Okay, how about this? If you have a heteroatom and it has no lone pair, or it has a positive charge, that's going to be electron withdrawing group. And last one, if you have a group, like an alkyl group, that alkyl group, it has, let's say, double bond or say a triple bond. Stuff like this. Because the hybridization here is sp or sp2, okay, they will be pulling electron density from the ring, and instead of hydrogen, okay, so hydrogen is giving electron, while carbon with sp or sp2 hybridization, they will be pulling electron density, so there will be electron withdrawing group. Now, how do I order these 3 groups? I have a heteroatom, nitrogen, okay, with high electron density, and I have 2 oxygen also attached to it. Okay, and remember, electronegativity to the right side of periodic table increases, down in any group decreases. And the more nitrogen oxygen atom you have, the stronger you will be pulling from the ring. So this one is going to be a strong electron withdrawing group. And how about this carbon? This carbon, it has sp2 hybridization. Okay, and how about the chloride? Chloride is the electron withdrawing group, but it has lone pair. Okay, how do I order this? This is going to be number 1. Okay, why? Because I have nitrogen with a positive charge on it. And how about this? I have carbon with sp2 hybridization. And this one, it will be number 3. Why? The third one is going to be number 3. Why do we say it's going to be the weakest one here? And remember, electronegativity to the right side increases. So I expect the chloride to be really strong electron withdrawing group. Yes, it's a strong electron withdrawing group. But keep this one in your mind. You do have a lone pair. Lone pair. And effect of lone pair is supposed to donate electron or share electron with the ring. So lone pair is going to enrich the electron density on the ring, but nature of chloride by itself wants to pull electron density from the ring. So we have 2 factors working against each other. Electronegativity is pulling electron density from the ring, but lone pair is trying to share electrons with the ring. So 2 factors working against each other, and that's the reason we say halide are deactivator, but they are weak deactivator. I'm going to show you a table for them. If you have a lone pair on heteroatom, you will have a strong activator. And if you attach a group with sp or sp2 hybridization, you will moderate, the strength. technically you are going to pull some electron density and electron density from the heteroatom, and the heteroatom it will be weaker, okay? Or we can say weaker in shared lone pair with the ring. And if you replace heteroatom by alkyl group, then you will have a weak activator. It still is activator, but weak. And look to the activator. All of them are directing to ortho and para position. Well, when it comes to deactivators, you have heteroatom with maybe a positive charge, or you have a carbon with halide groups attached to it. In that case, we say they are strong deactivator. They will pull electron density from the ring. And next one, what if I replace them here? Replace the heteroatom by carbon with sp2 hybridization. It will be mild, okay, milder than the previous one, but still is a sp2 hybridization. So that's going to pull electron density from the ring, and the ring it will be poorer than benzene. Okay, and a halide, as I said, they want to pull electron density from the ring, but because they have lone pair, they will share those lone pair with the ring, so they will be activator, deactivator at the same time, and that's the reason we call them weak deactivator. Okay, weak deactivator. And I made a mistake, and the mistake that I made, please ignore those because I just copy paste them. I copy paste them from the previous one, and deactivator they will lead to the meta position, except the alkyl halide, and except the halide that they will technically direct to the ortho and para position. And this is going to be the end of this lecture, and thank you very much.